The second derivative test is another way to determine if a critical value is a local maximum or a local minimum. You might also be familiar with the first derivative test, which allows you to draw similar conclusions using the first derivative, but this one will involve the second derivative. Let's say you have a critical value, which is a number c where the first derivative is equal to 0 because you have a horizontal tangent line. Then you check the second derivative evaluated at that number c. If the second derivative is positive, that means the function is concave up. If the function's concave up, that point f of c must be a local minimum. If you find the second derivative evaluated at c is negative, that means the function is concave down at that point. That point then must be a local maximum. Let's take a look at an example. Here we have the same example in my first derivative test video, so we can compare the results, but the work will look different because we will involve the second derivative test. You first find the critical values, and you begin by finding the first derivative to be able to do that. The first derivative f prime of x is equal to 6x squared minus 6x minus 12. You set your first derivative equal to 0 to find these critical values. You can divide the entire equation by 6 on each side. 0 will equal 2, x squared minus x minus 2. Factor the equation. Set each factor equal to 0, isolate the x, and you will get the x value of 2 and negative 1. These are the same critical values found in my other video. These are the critical values where the first derivative is equal to 0. Now the work will look different because we will perform the second derivative test. To do the second derivative test, you first got to find the second derivative, f double prime of x, which we will find by taking the derivative of the first derivative. And this will give us 12x minus 6. Now we test the second derivative evaluated at those critical values. So we're going to first take the 2, plug that into the second derivative. Let's find f double prime of 2, which is equal to 12 times 2 minus 6. 24 minus 6 is 18. What's important here is that this is greater than 0. We know the second derivative is greater than 0. That means the function must be concave up. So the conclusion we can draw then is that f of 2, when the number is 2 at that critical value, is a local minimum. And we did that by the second derivative test. Next, we got to check the critical value negative 1. We will find f double prime of negative 1. You got to plug the negative 1 to the second derivative on the second derivative test. 12 times negative 1 minus 6, which is definitely negative, technically negative 18. Being less than 0, if your second derivative is negative, that means your function is concave down. If you have a concave down function, that point, f of negative 1, must be a local maximum point. And we found this by doing the second derivative test. Let's confirm this local maximum and local minimum on a graph in a moment. Here we have that f of negative 1 is a local maximum, confirming that, and f of 2 is a local minimum. And what we did doing the second derivative test was to determine that for the f of negative 1, at the value negative 1, our second derivative was negative, meaning that function was concave down. When f of 2 was a local minimum, we found that by the second derivative evaluated at 2 gave us positive numbers, meaning the function was concave up. And when it was concave up, we determined that point was a local minimum point.